Now, we will discuss the architectural overview. This block diagram represents an overview of all device features and is not specific to any one device. The F28069 device is designed around a multi-bus architecture, also known as a modified Harvard architecture. This can be seen in the block diagram by the separate program bus and data bus along with the link between the two buses. This type of architecture greatly enhances the performance of the device. In the upper left area of the block diagram, you will find the memory section, which consists of the boot ROM, sectored flash, and RAM. Also, you will notice that the 6-channel DMA has its own set of buses. In the lower left area of the block diagram, you will find the execution section, which consists of a 32-bit by 32-bit hardware multiplier, a read-modify-write atomic ALU, a floating point unit, and a Viterbi complex math CRC unit. The control or accelerator coprocessor is an independent and separate unit that has its own set of buses. The peripherals are grouped on the right side of the block diagram. The upper set is the control peripherals, which consists of the EPWM, eCapture, EQEP, ADC, and Watchdog. The lower set is the communication peripherals and consists of the multi-channel buffered serial port, I2C, SCI, SPI, CAN, and USB. The PI block, or Peripheral Interrupt Expansion block, manages the interrupts from the peripherals. In the bottom right corner is the general purpose I/O. Also, the CPU has 3 32-bit general purpose timers available. The F28069 utilizes a contiguous memory map, also known as a von Neumann architecture. This type of memory map lends itself well to higher level languages. This can be seen by the labels located at the top of the memory map, where the memory blocks extend between both the data space and program space. At the top of the map, we have 2 blocks of RAM called M0 and M1. Then we see PF0 through PF3, which are the peripheral frames. This is the area where you will find the peripheral registers. Also in this space, you will find the PI block. Memory blocks L0 through L8 are grouped together. L0 through L3 are accessible by the CPU and CLA. L5 through L8 are accessible by the DMA. The user OTP is a one-time programmable memory block. TI reserves a small space in the map for the ADC and oscillator calibration data. The flash block contains a section for passwords, which are used by the code security module. The boot ROM and boot ROM vectors are located at the bottom of the memory map. The F28X devices feature a very fast interrupt response manager using the PI block. This allows up to 96 possible interrupt vectors to be processed by the CPU. We will cover more details about this in the Reset, Interrupts, and System Initialization module. The DMA allows data to be transferred between peripherals and/or memory without intervention from the CPU. The DMA can read data from the ADC result registers, transfer to or from memory blocks L5 through L8, transfer to or from the McBSP, and also modify registers in the EPWM. Triggers are used to initiate the transfers, and when completed, the DMA can generate an interrupt. The control or accelerator is an independent 32-bit floating point math accelerator. It executes algorithms independently and in parallel with the CPU. It has direct access to the EPWM, high-res PWM, eCapture, EQEP, ADC result, and comparator registers. It responds to peripheral interrupts independently of the CPU and frees up the CPU for other tasks such as communications and diagnostics. The Viterbi complex math CRC unit extends the C28X instruction set to support Viterbi operations used in communications, complex math, which includes complex FFTs, complex filters, and is used in power line communications and radar applications, and cyclical redundancy check, which is used in communications, and memory robustness checks. This slide lists a summary of the major architectural features covered in this module.